It's time for another section. This one on virtual memory is going to be a very important one for the course because virtual memory is a critical component of modern computers that allows us allows our programs to take advantage of the huge address space we can provide, especially with a 64-bit address, but still realize things on the limited amount of memory that we have. As always with our sections, we're going to start off with a quick overview and motivation for the topic, and then we'll get into some of the details of how virtual memory is actually implemented, how it serves as a great tool for caching at a different level than the caches we've already looked at, and how it helps with memory management and protection. Finally, we'll conclude with a detailed example of virtual memory in action. Okay, so you'll remember from the last section that a process is an instance of a running program. It is a really important idea in computer science, and there's two key abstractions that a process model provides. And that is one of logical control flow, namely that each process seems to have full control of the CPU. It does everything it needs to do and doesn't really worry about other processes that are running. That's what we learned about in the previous section, how we can interleave multiple processes and so on. The other key abstraction that a process provides is that it lets the programmer think about their process or their program running in that process as having its own private address space. An address space that is huge, 64 bits of addressing, and again, exclusive use of that memory. Now, that's not really true, of course, because we're going to be running multiple processes on the same processor. They're all going to want to use memory. So this is not going to be a perfect exclusive use. And then in addition, we're going to have a much larger virtual memory than a physical memory that we can really realize in the computer system. So virtual memory is going to help us with both of these things, exclusive use and a huge virtual memory, even when we have a small one. So let's take a look at what we know about virtual memory so far. So programs refer to addresses in memory, and these are really virtual memory addresses. So every time we write an instruction like this and use an address, in this case an address stored in the register ECX, remember the parentheses tell us to go to that address in memory and get the value stored there, move it to a register in this case. All right, what we're really doing is going to a 64-bit address, which may or may not exist physically in a particular place in memory, but exists virtually, in that we have this huge array of bytes. Each byte has its own address, and the system is going to provide a private address space for each one of our processes. Okay. The compiler and the runtime system are going to worry about how to allocate stuff in memory. We've seen this already to a certain extent. We'll see a little bit more later on. But basically, the compiler is deciding where different program objects should be stored in that large array of memory, and where data should be stored, and so on. So what problems does virtual memory solve that physical memory doesn't solve for us? Okay, so the first problem is that how does everything fit? We have this huge address space, 64-bit addresses, 16 exabytes of data. We don't have computers with that much physical memory. The physical memory we have is a tiny, tiny amount compared to that address space. So how do we fit all of this stuff that could be in here for our programs into this tiny little space? Clearly, we can't fit it all in at the same time. We're going to have to decide what to put in when. And that is one of the important things that virtual memory is going to do for us. Another aspect is that we have multiple processes, each one of them thinking they have that huge address space. Each one of them has a bunch of things in memory. It's stack, it's heap, it's program, and it's data, static data. And what is going to go where in the physical memory, that little piece of physical main memory? How are we going to fit it in there? And how are we going to multiplex between all of these so that when one process is running, its memory is available in physical main memory, and when a different process is running, its memory is available. And those have to be kept separate and distinct. So we're going to want to protect one process from another, in that if one process has a portion of memory that it uses, we don't want to have another process write to that and maybe clobber data that the first process needed. Okay, so we got to keep these separate from each other and protect them from each other's interactions. And then the flip side of that is that we also may want to share memory sometimes. For example, suppose that we have a chunk of memory that represents a shared library of code. So quick example, right? Those printf and scanf routines that are commonly used by C programs. We don't want to have to put those in memory multiple times. So we'd like processes to be able to share those pieces, especially if they're read-only, right? That we're not writing new values to those locations. So this is an important aspect of sharing parts of memory and making it more efficient for the small physical memory to handle many processes.